We have already discussed the use of an atomic force microscope probe for manipulating and measuring single molecules. That's the first entry in this table. This technique is widespread because instruments are commercially available, and it has high spatial resolution in the sense that one can do force measurements on some predetermined point on a complex sample. The drawback, though, is that the stiffness of the probe is quite high, and therefore the sensitivity to very weak interactions small. A sort of equivalent to the AFM, not currently commercially available, is to use very long, flexible, pulled glass pipettes or rods that have a molecule or a cell, for example, suctioned into the end of them, maybe a molecule on a flexible tether, which can then chemically react with a second pipette, which has some functionalization on it to grab the molecule, so that one can form an elastic junction in which the molecule spans these two pipettes, and then one can observe the deflection of the pipettes under an optical microscope as you move one away from the other. Knowing the spring constant of the two pipettes, one can deduce elastic properties of the molecule. You see here that the microneedles can have spring constants as small as a piconewton per meter. Another way of doing these experiments is hydrodynamic flow, so that, for example, one could tether, let's say, a DNA molecule to a surface and at the other end to a polystyrene latex sphere, and then just flow fluid like this and observe the stretching of the fluid, of the bead, or the motion of the bead as a function of the velocity of the fluid, knowing that the force on the bead from Stokes' law is proportional to the velocity of the fluid. Magnetic beads are another very useful technique, and we'll say something about these in the last slide of this chapter. But mainly I'm going to talk now about the use of optical fields as single molecule manipulation tools. So it was observed many years ago by Ashkin that dielectric spheres tended to move into the focal point of a laser beam. The spheres have to be transparent and large enough, that is on the order of a few microns in size, for this phenomenon to be observed. One can understand this the following way. Supposing a fluctuation were to pull this sphere down, it would now receive more light on its bottom side, and the light that hits the sphere is refracted through it like this, with the result that there is a net impulse on the sphere in this direction, owing to the finite momentum of the photons passing through it, because the photons have been deflected in this way. The consequence is to push the sphere back to the center. There is an opposite effect. If the sphere were to fluctuate up this way, then it feels more light hitting it here and gets pushed back to the center again. There is an equivalent effect in the z direction, although the effective spring constant confining it in z is much smaller. For just a few milliwatts, the example I'm giving here is 10 milliwatts on a well-focused laser beam and say a 10 micron diameter polystyrene latex sphere, the spring constant on the trap is of the order of 10 to the minus 2 to 10 to the minus 3 newtons per meter, much less than an AFM. Now, the resolution of these measurements, of course, is limited because the product of the force on a bead and the thermal fluctuations, of course, is 4.2 piconewtons nanometers at 300 Kelvin. And this means, therefore, that if, for example, you're exerting 4.2 piconewtons on a bead, its thermal fluctuations would be a nanometer, and that would be the limit of the spatial resolution to which one could locate the center of a bead in an image. These beads are located by fitting their image with a computer program, much as point source fluorescence molecules were located in the module on fluorescence. So here's an illustration of how a trap works. So the idea is to take a bead and trap it in a suction pipette. And the bead will have been pre-functionalized with a limited number of molecules, let's say long DNA molecules, which have at the end some reactive group. The bead in the optical trap, so I'll show the laser schematically, it's not evident on the slide here. The bead in the optical trap has some groups that react with what I've shown as R. And so if you bring these two together and try touch the spheres together and then pull them away again, when eventually you have a contact, you'll see the bead in the trap begin to be pulled by the bead on the suction pipette. So here is an optical micrograph, but let's show you a movie of this in effect. Let's run that again. So you see we're moving the bead in the trap. If we pull hard enough, we pull the bead right out of the trap. And so from the motion of the bead in the trap and knowing the force constant of the trap, we can calculate the force on the molecule. We know how far this pipette has gone, so we can generate a force distance curve for stretching a single molecule. Now to do this, we need to calibrate the force constant of the trap. One way to do this is just to flow a fluid through the little cell and use Stokes' law as correcting for being close to a surface, so simply to displace the bead by fluid flow. A very nice way of doing this is just to observe the noise fluctuations of the bead, though. This is the second method here. And so what one does is simply to monitor the position of the bead to very high resolution in a charged coupled device camera, and you'll see it Brownian motion, which I'm sort of showing here. And if you plot the power spectrum, so this is proportional to the displacement squared, as a function of frequency, one sees a 1 over f squared type of response, where the corner frequency here, where the power spectrum falls to half, is called Fc, and this can be used directly to calculate the spring constant of the trap, knowing the friction coefficient on the bead from this equation here.